Have you ever really stopped to wonder what's actually going on inside your computer? I mean, deep inside the chip, when you run a program, how does it go from your code, your click, to, well, to action? Today, we're going to pull back that curtain. Using some great research material from Dr. Sudheendra S G, we're going to walk through step by step how a computer's brain, the CPU, actually follows your commands. This is perfect for any educator out there looking to really demystify computing for their students.
So yeah, let's dive right in. We are not just talking theory today, not at all. We are going to get our hands dirty, so to speak, and watch a tiny, custom-built CPU literally come to life, processing a real program right here, right now.
Okay, so first things first, what are we actually feeding the CPU? What is a program really at its most basic, fundamental level?
Honestly, you can just think of it like a recipe. That's it. A program is just a list of very, very simple steps. We call them instructions, and they're all just laid out in the computer's memory, waiting. The CPU's only job is to follow that recipe, one line at a time, no questions asked. Now, each one of those tiny little steps, each instruction, is itself made of two smaller parts. For our little CPU, the whole thing is just an 8-bit command. The first part is called the opcode. That's the verb, the action. It tells the CPU what to do. And the second part is the operand. You can think of that as the noun. It tells the CPU what to use, like a piece of data, or maybe a location in memory. And this shows you the structure perfectly. You've got the first 4 bits for the opcode and the last 4 bits for the operand. It's just a clean, simple command. So for example, an instruction like 00101110 could mean load data. That's the 0010 part, from memory address 14, which is 1110 in binary. See? Action and a subject, all packed into one byte. Okay, so let's head down to the engine room and see how the CPU actually juggles all these instructions. I mean, how does it keep track of where it is in the recipe? Well, the CPU uses 2 incredibly important little tools to manage the flow. The first one is called the program counter. You can think of it as the CPU's bookmark. It always points to the memory address of the very next instruction it needs to grab. And the second tool is the instruction register, which is kind of like a temporary clipboard. It holds on to the current instruction while the CPU is working on it. So this all comes down to a simple 3-step dance. And this is the absolute heartbeat of every computer out there. First, it uses that program counter to fetch the next instruction from memory. Second, it decodes that instruction to figure out, okay, what am I supposed to do? And third, it executes the command. Then the program counter clicks to the next number, and it does it all over again. Fetch, decode, execute, over and over and over. All right, enough theory. It's time to see this thing in action. We're going to load a tiny little program into our CPU's memory and just watch it run step by step. Okay, here it is. This is our entire program, sitting there in RAM. Our goal is super simple. We're going to add the number 3 and the number 14. You can see our 4 instructions right at the top, at addresses 0 through 3. And then down at the bottom, at addresses 14 and 15, that's our data, the numbers 3 and 14. The whole mission is to do the math and store the final answer at address 13. Okay, here we go. Cycle 1 begins. The program counter is pointing at address 0, so the CPU fetches that first instruction, 00121110. Then it decodes it. The opcode 0012 means load something into a workspace called register A, and the operand 1110 tells it to get that something from memory address 14. Okay, time to execute. And boom, there it is. The CPU zips over to address 14, grabs the value stored there, which is 3, and pops it into register A. Step 1 is done. And just like that, the program counter automatically clicks over to 1, ready for the next command. All right, next up, the program counter is at 1. The CPU fetches the next instruction, 00011111. The decode is simple. It means load a value into the other workspace, register B this time, from memory address 15. And just like that, it grabs the value 14 and loads it into register B. Perfect. Now both of our numbers are locked and loaded inside the CPU, and the program counter ticks up to 2. Okay, here comes the main event. The CPU fetches the instruction at address 21000100. Now, here's what's cool about the decode on this one. The opcode 100 tells the special calculator part of the CPU, the Arithmetic Logic Unit, to use the values that are already sitting in the registers. So, the ALU immediately adds them up,
3 plus 14 equals 17. It then stores that result, 17, back into register A, overwriting the old number. The calculation is done, and the program counter moves on to our final instruction at address 3.
So we've got our answer, but it's still kind of trapped inside the CPU. This last instruction is what gets it out. The CPU fetches 01011101 from address 3 and decodes it as a store command. Take whatever is in register A and save it to memory address 13. And it executes. The CPU writes the number 17 into memory location 13. Mission accomplished. Now, in a real program, you'd absolutely need a halt instruction right here, because without it, the CPU would just keep on going, trying to execute whatever random bits and bytes it found next, and, well, that usually doesn't end well. But, programs do a lot more than just run in a straight line, right? The real power, the thing that makes them feel smart, is their ability to make decisions and repeat tasks. So, how do they do that? They do it with something called jump instructions. An unconditional jump is simple. It just forces the program counter back to an earlier spot in the recipe, creating a loop. But the conditional jump, that's where the real magic happens. It only jumps if a certain condition is true, like, say, if the last calculation resulted in 0. This right here, this is the bedrock of all decision-making in software. If this, then that. And this brings up a fascinating question, right? If a basic CPU can only really do simple stuff like add and subtract, how in the world do we get complex operations like division? Well, the answer is software. By cleverly using these conditional jumps and loops, a program can actually perform division by just doing repeated subtraction. Now, our tiny CPU is a fantastic teaching tool, but let's be real. How does this little guy relate to the absolute monster of a processor that's inside your computer right now? Well, the difference is just scale. It's not a different principle. Our CPU knows about 16 instructions. A modern Core i7 knows thousands. Our CPU can talk to 16 memory locations. A modern one can talk to billions. But, and this is the key, the core heartbeat is exactly the same. Fetch, decode, execute. And really, that's the ultimate takeaway here. All the incredible complexity of the software you use every single day, it's all built from these mind-bogglingly simple, logical steps, just executed one after another at a blinding speed. It's how a laundry list of tiny instructions becomes a powerful program. And that, right there, that's the magic of computing.